Welcome back. We're still talking about chemistry. We're going to be getting into bonding and how elements, atoms bond together. This is a little outline for this lecture. We're going to go over some simple stuff like the atomic number and mass. We already touched on that. Get into isotopes, talk about carbon dating a little bit. Then we'll talk about Niels Bohr diagrams. Again, Niels Bohr won a Nobel Prize for his work, kind of talking about atom structure. And then we will talk about molecules, compounds, formula, types of bonding, ionic versus covalent versus hydrogen. Lot to cover in this one, so let's get to it. Atomic mass and number. So we talked about this a little bit. Let's go right to carbon. So this, on a periodic table, this number here is the atomic number. The atomic number of carbon is always 6. It will always be 6. It's forever 6. And this represents the protons, which will also equal the number of electrons. And this changes the properties of the atom. And we'll talk about why. This number down here, the atomic mass, this is the atomic mass. Atomic mass. This is equal to the protons plus the neutrons. If you remember, that's the atomic mass, that's the atomic number. If you remember, if we think of the mass, the protons and the neutrons really are what make up the mass, right? So that makes sense. Whereas the protons and electrons have to equal each other because these charges have to cancel out. And electrons weigh essentially nothing, 1/2000th of whatever a proton or electron does. So they don't really contribute to the mass. Even if you had 100 electrons, it's still essentially acting as nothing compared to all those protons and neutrons. All right, so we talked about atomic mass and atomic number. That's what those are. So, for example, oxygen, its atomic number is 8. It's the 8th element, and its mass is about 16. 8 plus 8. Pretty nifty how that works. Okay. Great, so we did that, check that off. Boom, atomic mass, atomic number. Isotope, so what is an isotope now? Well, let's just talk about carbon. So we can have something called carbon-14, and we can do carbon dating. So sometimes, let's go ahead and let's draw out a carbon atom. What colors was I doing? The protons. Protons I was doing in blue, neutrons I was doing in gray. All right, so we got carbon is 6. 1, 2, 3, 4, 5, 6. All right, we got 6 protons. We're going to have 6, 1, 2, 3, 4, 5, 6. And they wouldn't look exactly like this, but we got 6 neutrons. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, boom, that's a carbon atom. That's a nucleus of a carbon atom. I'm not going to draw on the electrons, but they're there. All right, so the atomic mass or the atomic number of this would be 6, right? Whoop. What is going on? Oh, this is acting as a movement key and not a number key. That's strange. Okay, so our atomic number is 6. Atomic number is our protons. All right, and our atomic weight was what? It was the weight of our protons essentially plus the weight of our neutrons. So our atomic mass would be, we have 6 plus 6, so our atomic mass would be 12. Why is that doing that? It's tripping me up. This would be 12. So our atomic weight, or atomic mass, sorry, is protons, the mass of protons plus neutrons. All right, so we can have something called an isotope. And an isotope is an atom with more or less neutrons. So we can adjust the number of neutrons. So for example, take this, and we can add, let's say, 2 additional neutrons to it. Let me zoom out so they're about similar size. Or I can just copy and paste these little bad boys. Look at that magic of computing. Boom. Boom. So now we got 2 extra neutrons. This is still carbon because we've not changed the atomic number, because the atomic number is the number of protons. So our atomic number is still 6, right? But now our atomic mass is going to be 14. Oh boy. That is really tripping me up. I don't know why it's doing that. Okay, atomic mass is now 14. This would be carbon 14. You can do something called carbon 14 dating. So sometimes in the atmosphere, you'll have CO2, let's say, that is an isotope of carbon. So it'll be carbon 14. And over time, this will decay. And what that means is that over time, what will happen is one of these neutrons will leave it, it'll fall off. Oh boy. I have to grab this one. And when it does that, it usually releases a little something called radiation in the form of energy, like that. So it will release radiation. And we can detect that. We can detect that radiation. So we can then see how much of this is left in, let's say, an old tree stump or something like that. Or a rock, let's say, something like that. So we can use this to kind of understand how old things are. And it's very useful that. So this isotope is now, it's called decaying. It will decay over time and release radiation, which is just energy that we can detect. Radioactive decay. That's what that's called. Radioactive decay. We can use this to date how old things are, because we know the rate at which this happens. We know the rate at which this decay occurs. And depending on the element, different elements will decay faster or slower. This is also this loss of neutrons, and then this neutron can actually then, we're going to be getting a little weeds here a little bit, but if you go way down here, to something like uranium, this is a big boy, 92. It's got 92 protons. So it's going to have 92 neutrons, and then if you have a couple more neutrons on there, and you purify all that, so you got these isotopes of uranium. It's really hard to do. That's the hard part of making an atomic weapon. And then you clump all those together, but you don't. You have kind of like a let's say like this much. It's not going to be this much, and then you have another little bit like this, and you smash it in there. Then you get this chain reaction where these neutrons are all coming off. They're banging into other atoms like this, and when that happens, then this neutron comes off and it bangs into another atom, and it bangs into another atom, and then that blah, 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 blah. It's called a chain reaction. It's called critical mass when you have that certain level of mass, and that's what a nuclear weapon is. It has to do with isotopes of those very heavy elements that can decay rapidly. All right, kind of got in the weeds there, but I like talking about nuclear weapons. They're pretty cool, even though they're extremely destructive, and we are the only country to ever use them on another country. So I think that's an interesting thing to remember. We use nuclear weapons against the world. Okay, isotopes, carbon dating. All right, let's go over Bohr diagrams again. All right, so we'll do carbon again. Yeah, we'll do carbon here, because we just did it. So we got 6 protons, right? Which means we also have 6 electrons. So now we're going to do some Bohr diagrams. of carbon. All right, and we will do carbon. We'll just do it in this color. So carbon. So when you do a Bohr diagram, you just write the letter of the atomic symbol is what that's called. The letter. This is the atomic symbol. Put this over here. This is the atomic symbol. Okay. All right. So we put the atomic symbol in the middle, and it has 6 protons in there and 6 neutrons. And then it's got these valence, or these orbitals around it, is what they're called. So we got this first orbital, which is going to contain 2 electrons. So the first orbital can only ever contain 2 electrons. And this is true. This method that I'm showing you is true for the first 20 atoms on the periodic table. Once you get past that, it gets a little weird. All right, and we can hold 2 electrons in that first orbital. And then we can expand out a second orbital here. And every orbital after that can hold 8 electrons. But carbon only has 6 electrons total, so we only need to draw in 4 here. 1, 2, 3, 4. That's a Bohr diagram. So this first orbital, let's just draw it in these little notes that I just said. First orbital can hold 2 electrons. Every orbital after that can hold 8. Okay? And every atom wants to have a full valence shell. What does that mean? Valence shell is the outermost orbital. Okay, so let's just do a couple more of these. We'll just start with good old hydrogen, our good old pal hydrogen. So we got hydrogen, we got our first orbital, and hydrogen's atomic number is 1. Okay, so it's got 1 electron there. All right, hydrogen, okay, every atom wants to have a full valence shell, its outermost shell. The first orbital can hold 2 electrons, 1, 2, all right, carbon's good there. Hydrogen only has 1 electron there, so it is not full. It does not have a full orbital. So hydrogen is not happy that way, not happy at all. All right, now let's look at, let's look at helium. Helium's atomic symbol is He. Its atomic number is 2. So it has 2 protons and it is going to have 2 electrons. All right, helium, remember, its atomic number is 2. It's a noble gas. They don't react, non-reactive. Helium number 2. All right. Helium, 2 electrons. This is its outermost shell. Every atom wants to have a full valence shell, its outermost shell. Helium's got a full outer shell. It doesn't need to react with anything. It's happy the way it is. Hydrogen, on the other hand, would like to react with some stuff. It also really likes to just get rid of that electron. Carbon, all right, let's look at carbon. So this orbital can hold 8. How many does that have? 1, 2, 3, 4. Every atom wants to have a full valence shell, which is its outermost shell. Does carbon have a full outer shell? No. It's only got half of it full. So it would love to react with some stuff and fill that in. And this method of drawing atoms works for drawing pretty much any atom up to number 20. Things get a little weird. So we can draw all the way up to calcium. Let's actually draw sodium right now. So sodium is 11. Sodium's atomic symbol is Na. Talk a little bit about the importance of that. someday in the future. So we got nah, brah. All right, we got our first valence shell, our first shell, orbital, sorry. It's not a valence shell, it's just an orbital. And let's fill that in. So remember the atomic number here is 11. So we need 11 electrons. So we got 1, 2. All right, buckle my shoe. All right, nope, wrong color. All right, then we got this guy. All right, so we got 1, 2. And now we need, so that's going to be 2, and then we can add 8 in here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's a total of 10. So we actually need 1 more shell. And I'm going to do a little fancy schmancy copy pasty snasty like a snapey. All right, listen up, babies. Watch out for bats, you'll get rabies. Boom. All right, let's count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Atomic number for sodium, 11. All right, that's a sodium. So sodium, look at it. Let's talk about sodium here for a minute. Every atom wants to have a full valence shell, its outermost shell. Okay, this thing is dang near empty. It's only got 1 in it. So sodium is really going to want to get rid of that. All right, and we'll talk a little bit about that in a second. Let's now talk about some basic little terms here. And sodium is also going to be, you could just see, like, from looking at this, it's going to be a lot bigger than something like hydrogen. Hydrogen and helium, they only have these little one orbital, which is their valence shell. Whereas when sodium, you get up to 11, now you got 3 orbitals. Pretty nifty how that works. Okay, so now let's go through molecule, compound, and a formula. And then we'll get into the types of bonding. All right, so we went through this a little bit. So a molecule would be when you have more than 1 atom coming together. And we'll copy a couple hydrogens here. We'll use those as our little example. So a molecule is 2 or more atoms coming together. It's beautiful. It's really, really beautiful. All right. Molecules, 2 or more atoms coming together. And here we have an example of hydrogen. And what I'm going to do is I'm going to put these electrons kind of on the same side, like so. And then I'm going to bring them together, like that. So now we have something called, this would be H2, and really the 2 is drawn kind of below. I'll draw it by hand below. I can't really do subscripts in this program. H2. And this is hydrogen gas. So out in the air, the Hindenburg blimp that blew up and caught on fire, that thing was full of hydrogen gas. It's very, very flammable. So you don't want to use this to fill up balloons. That's why we use helium to fill up balloons and not hydrogen, because this is very, very flammable. But unless you add a flame to this, it's stable. This hydrogen likes to hang out with itself. It's now happy. Because these are now sharing the electrons. I'm kind of skipping ahead a little bit, but a molecule is 2 or more atoms that come together. They're bound to each other. That's a molecule. There's an infinite number of molecules out there. That's just one example. Okay, so a compound is the same as a molecule. A compound is a molecule but it has more than 1 type of atom in it. Does that make sense? So this is not a compound. It is a molecule, but it's not a compound. Compound. Let's talk. Let's do one we'll draw out the formula. So this is the formula of this. We'll draw out the formula of what we're going to draw here. This would be CH4. And this would be methane. So this is methane. This is what cows burp and we fart. It is a greenhouse gas. It is also highly flammable. And methane is made out of a carbon atom in the center. So we got carbon in the center. Carbon has its 2 orbitals, like so. And then we are going to have 4 hydrogens, right? 4 hydrogens around it, like so. And they are each going to have their little orbital, electron orbital, like so. Okay, so now we need to draw in our, I'm going to draw these electrons in different colors just to make it clear. We've got our carbon's electrons, which are 1. Need to make them the big boy. 1, 2, and then it's going to be 1, 2, 3, 4. And then we can have our hydrogen's electrons getting added in. 1, 2, 3, 4. So now if you look at this, we've got a molecule. It's made out of more than one type of atom, right? It's made out of carbon and hydrogen. CH4, we got carbon and 4 hydrogens. And if we look at this outer shell of carbon, it's got 1, 2, 3, 4, 5, 6, 7, 8. So this molecule is pretty happy because every atom wants to have a full valence shell, its outermost shell. All right, so that carbon's very happy like this. And these hydrogens are also happy. They each have 1, 2, 1, 2, 1, 2, 1, 2. Oh, so beautiful. So that's a compound, and this is a formula. One formula that I want you to know. So if a chemical formula is this. It's this little. So we could draw a couple more. Let's just do another one. We all know this one. H. Oh, that looks a little wonky. 2. It still looks a little wonky, but whatever, we'll live with it. And then O. That would be obviously water, H2O. It's a little funny looking, but you get it. That's the chemical formula for water. Chemical formula for water. Beautiful. And one I want you to kind of just be aware of and know, because we'll be talking about this one kind of throughout the semester, is C H O. I was trying to think how exactly I wanted it. So it's C6 H12 O6. So that right there is a very special chemical formula, C6H12O6, and I'll always kind of have that, those ratios there. This is the chemical formula for glucose / sugar, right? Which is like one of the main energy sources for life. C6H12O6. Anytime you see that, we're talking about a sugar, we're talking about glucose. Very beautiful. All right, we talked about Bohr diagrams. Any atom up to calcium you can do this for. We talked about, where are we? We talked about molecule, compound formula, types of bonding, and now we need to talk about these different types of bonding. All right, ionic versus covalent versus hydrogen. All right. Well, the good news is we've already talked about covalent bonding. So covalent bonding is when covalent shell, covalence shell, covalent, sharing, cooperative. Sharing is when atoms share electrons in their valence shells. look at this. We've already drawn these out. So these two that we've drawn right here and everything that we've drawn so far in this class, those are covalent bonds. So hydrogen gas here, these are sharing these electrons. So these electrons are really spinning around here, and then they're spinning around there. And this one's spinning around here, and then it's spinning around there. So they're sharing these electrons, and you don't ever know which atom they're in until you measure it, and then when you measure it, you don't know anything else about it because you've now stopped it, you've perturbed it, you don't know how fast it's going, you don't know any of its other properties, but you just know where it's at. Okay, same thing over here. These valence electrons, like this electron here, it could be here, it could go over here, it could be over here, it could be over here. All of these are now sharing these electrons in this kind. They kind of like become one big atom, and those electrons are all whizzing around in these outer shells of all of this giant molecule-sized atom now. That is what covalent bonding is. Covalent bond is when atoms share electrons in their valence shell. All right. Okay. I'm going to recopy this little guy down here because we're going to talk about ionic bonding now. So you can redraw this quick. So sodium really likes to bind with chlorine in a special kind of way. So we're going to talk about now ionic bonding. Ionic bonding is when atoms gain or lose electrons, donate or receive, and gain a charge as a result. Okay, so sodium really likes to bind to chlorine. Let's go over to chlorine. So sodium we already drew. Sodium is a number 11, atomic number 11. Chlorine is 17. All right, so we got to draw a chlorine atom here. We got to draw a little Bohr diagram of chlorine, 17. So this boy's going to be a little bigger than even this. And chlorine, let's actually make it in red. Sounds good. Chlorine. So we're going to have 2 there. And then 8, that'll make 10. And then another 8 can make 18, right? It was 17, so we can get all the way there. Okay, great. Perfect. So then we're going to have our 2 here. Oops. We are going to have our 2 in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, and then we're going to have another 7 out here. 1, 2, 3, 4, 5, 6, 7. All right, so that's our chlorine ion. All right, so if we look at this valence shell of this sodium, and we look at this valence shell, this has 1 electron in valence shell. Oops. Shield. 1 electron in valence shell, 7 electrons in valence shell. All right, is this starting to click here? What's going to happen? Every atom wants to have a full valence shell, which is its outermost shell. All right, well, we could fix that for both sodium and chlorine if sodium just got rid of this electron and chlorine stole it. And guess what? That's exactly what happens. So this electron jumps over into the shell, and make that a slightly different color just so we can see that. So sodium donates electron. Like so. And I'm going to just copy these and paste these. You don't necessarily have to redraw this exact part here, but you can. Okay, so now this electron is now over here in that shell. This orbital is now deleted, And now we have a charge associated with this. So this lost an electron. Electrons are negative, right? So now this boy going to be positive over here. We're going to have a positive charge on this sodium. Positive ion. And this chlorine now gained an electron. Electrons are negative. So this is going to be negative. We now have a negative ion. So ions like this have a charge. Okay? Pretty nifty. Okay, so that's an ionic bond. Pretty cool indeed. And these, so now since these are positive and negative, they will like to stick around each other. They will form a crystalline-like structure. So chlorine is going to be much larger. Just kind of draw what this would look like. So we'll draw chlorine in red. I'm just going to draw that as a circle. And then this is surrounded by like a bunch of sodiums. And these kind of fit in together. Sodiums I drew in purple. Yeah, something like this. We'll see how this looks. I've not actually drawn this out before. And then there would be then this guy. Let's see if I can copy it like this. Yeah. Yeah, that's not looking terrible. All right, and then I could do it like this. And they form this like beautiful square shaped. Oh, I need to get rid of that one. Sodium and chloride, they form these square-like crystals, where they arrange themselves as a solid into, what is going on? Into cube-like shape. So if you actually go into your kitchen and look at your salt, go look at your salt. And if you look at the cubes, I can bring some salt in the lab if you guys want to see it. They're all squares. They're squares. And then if you break those squares, they're squares. And if you break those squares, they're squares. And that's because the crystal structure, just like water forms hexagons, sodium and chloride form squares. It's pretty cool. So these will all be positive. These will all be negative. And so then they'll, based on their size, they form these square-like structures. And I'll pull up this little picture here just so you guys can see this. With your eyeballs, with somebody that drew it better than me, and then also we can see these salt crystals. So yeah, these are the square salt crystals. You see they make perfect little cubes. They're not necessarily always square, sometimes they're rectangular. And that's based on the sodiums wanting to pack in with the chlorines in this perfect little array, and they want to interact with each other because not because they're sharing electrons, but because now they've donated electrons between one and the other, they now have this charge, and that charge is what's sticking them together. So that's an ionic bond. Okay, and last but not least, we need to talk about hydrogen bonds. And I know I've gone a little long here, and I apologize for that. But we need to talk about hydrogen bonds. So we got covalent bonds here. We've got ionic bonds here, and now we need to talk about hydrogen bonds. And hydrogen bonds, you guessed it, usually have to do with water. So water is H2O. Let's draw the O in the center. O. Oxygen is atom number 8. So it can have 2 shells here. And we've already drawn this one before, but we're going to draw it again. Boom. We got our hydrogen, and we got our other hydrogen. They're each going to have their little shell. And remember, this kind of makes a little Mickey Mouse looking guy. Little sticky Mickey Mises. That's what water is. And we will draw our electrons in here nice and beautifully. Boom, boom. 1, 2, 3, 4, 5, 6. And then our hydrogens, electrons will look something like that. Okay, so we got a covalent bond here, right? Because they're sharing electrons. There's no donation of electrons. All right. But oxygen in here, if we were to remove that, remember it has actually 6 protons in here. So it actually has 1, 2, 3, 4, 5, 6 protons. That's a lot of positive charge down in that nucleus compared to hydrogen, right? It's got 6 protons. Oxygen has 6 protons in the nucleus, meaning the shared electrons will tend to be more attracted, will tend to spend more time in oxygen's electron orbitals. Oxygen's orbitals, we'll just say that. Orbital. It's called electronegative. That means oxygen is electronegative. Oxygen, this means this is referred to as oxygen being more electronegative than hydrogen. All right, does that make sense? So what does this mean? What does this mean? So if we were to kind of spin these little electrons around, like so, it'd spend a lot of time, more time over here, more time. I messed that all up. Spending more time. And then maybe when it goes through here, it's like, I can't wait to get back to the oxygen. Oh, yeah, feels good over here. Look at that. I'm around these protons. Oh, I love those protons in there. Yeah, I don't want to be there. I want to be down in here. So what that means is that oxygen, because of this property, it's going to have, this is a Greek letter for delta. It's going to have a delta negative. Delta means partial negative charge actually over here, because it's going to, the electrons are spending more time there. And these hydrogens are going to be delta positive. Slightly positive. And this is for both of the hydrogens. Okay? So they're slightly positive and slightly negative. So this is where we get the stickiness in water, which we're going to talk about more in the future. Little tiny sticky Mickey Mises. All right? All right. So if these are slightly positive and these are slightly negative, what does that mean if we have multiple water molecules sticking together or in the same vicinity? Let's just redraw some water molecules over here. So we've got, we'll just draw them as like little simple spheres. All right, so I've got my little water molecule looking like that. And then I got another one, maybe say looking like this, like that, like this, like that, and it's like this, or like that, like this, and it's like this. So just chill. Till the next episode. Oh, I do want that. Okay. And we'll draw one more. And we'll draw... Oops. Oh boy, what am I doing? No. Stop. Drop. Shut them down. Open up shop. Okay. And we'll draw it like here. Yeah, well, actually, you know what? I'm going to draw 2 more. We're just going to make this... We'll make this happen. And we'll draw one over here. So now we got liquid water here. We got these kind of close water molecules. And all of these are slightly positive, if you remember. These are slightly positive. I'm going to just draw them as little pluses. We talked about this a little bit at the beginning. So we got like little magnets going on here. And then these are all slightly negative. Oops. Right? and draw it off to the side here. These are all slightly negative. And so we've got a little magnet-like action happening. And the way we represent, what this is called is a hydrogen bond. And the way we represent it is like so. So we draw like little dashed lines of interaction between these water molecules. Okay, so these are slightly attracted to each other. And this guy's maybe a little far away. I'm going to bring him in a little bit. And each water molecule can have 4 of these actually. I'm only drawing 3 here. Let's just seal the deal here. We'll draw 1 more down here. Like so. So this is a hydrogen bond. And it's created by the partial charge across a molecule. And it involves hydrogen as one of the atoms, because hydrogen only has 1 proton. So that these electrons, they don't really want to spend a lot of time around 1 proton. They'd rather spend it around 6 protons. You know, they just vibing out better that way. I don't like how thick that is, but okay. All right. I know I went a little long there, but we had a lot to cover. We did it. Did we do it? Yes, we did. Yes, we did. We covered all of those. Fantastic. Look at that journey. We talked about nuclear weapons and then little sticky Nicky Muses. I mean, what else? What more could we ask for? That was probably 30 minutes. Oh, God, I'm sorry.